First, I would like to thank the organizing secretary, Dr. G. Srinivasagan, Mr. N. Ramesh, Vice Principal and Head of the Department of Chemistry, and the technical support team. And finally, the Rajabalayam's Rajas College management for this opportunity to connect you all through this webinar. Today, the topic of webinar is modern analytical techniques for chemical analysis. We all came across with a lot of spectroscopic techniques which use a wide spectrum of electromagnetic radiation. For example, we use ultraviolet radiation in UV spectroscopy, infrared radiation in Fourier transforms infrared spectroscopy, radio waves in nuclear magnetic resonance spectroscopy, and X-rays in X-ray diffraction and X-ray photoelectron spectroscopy. But here we are going to learn about a new spectroscopy based on synchrotron. Before getting into this analytical technique that is specifically called NEXUP, near edge X-ray absorption fine spectroscopy, which is based on a synchrotron, we will see what is a synchrotron and we will learn what is its working principle. So we all know about particle accelerator. In particle accelerator, particles like electron, protons, and ions, positive and negative ions, are accelerated to almost speed of light. When these particles attain the speed of light, they are used to bombard on the material of our interest, and we can able to see what the changes is happening by monitoring and detecting the changes by using the detector. One such accelerator is shown in this figure, that is called a LINAC. One such accelerator is shown in the figure, that is called a LINAC, which is abbreviated as linear accelerator. If you see in this figure, in the LINAC, there is a particle source through which a particle is fired. This fired particle will take the path of the particle B path and it will reach the target. So, in this case, we want to accelerate the particle. So, for accelerating the particle, we are using these channels C1, C2, C3, C4, and by changing the polarity in the channels, we can able to accelerate the particles. For example, if you take this source as an electron source, when the electron is fired from the source gun, the electron will enter a positive channel, and immediately after entering the positive channel, the polarity of the channel will change to negative. By doing so, the particle will tries to move out of this channel and it will tries to reach the next positive charged channel. So the basic principle in the acceleration is like charges repel each other and unlike charges attract each other. By using this principle, the electrons was accelerated in the linear accelerator. Next figure is, this is the real figure of aerial view of Stanford Linear Accelerator Center. This linear accelerator is about 3.21 kilometers, which was commissioned in the year 1962. Using this accelerator, 3 Nobel Prize was obtained. That is, the first one is for the discovery of the quark, that is in 1976, and the second one is for the discovery of the quark structure, that is in 1990, and the third one is for the discovery of the tau leptons, that is in 1995. So it is a very big instrument. Similarly, you have another particular instrument that is called a cyclotron. The main difference between the linear accelerator and the cyclotron is, in cyclotron, the particle is rotating in a circular path of varying radius. This instrument is also very big, and you can able to see this figure here. This is a tri-university meson facility at the University of British Columbia in Canada. This instrument diameter is around 17 meters, and the ion which is used for acceleration is H minus ions, which is having an energy of around 500 MeV. Next, the particle accelerator is synchrotron, which is we are much interested in learning about that. The synchrotron is basically an electron particle accelerator. Yes, by definition, a synchrotron is a large machine about the size of a football field that accelerates the electron to almost the speed of light. As the electrons are deflected through magnetic fields, they create extremely bright light. This light is channeled down beamlines to experimental workstation where it is used for research. This is the definition for the synchrotron. What does it mean is, no particle can able to reach the speed of light, right? When we are trying to make the particle to travel to the speed of light, it will lose its energy. It will lose its kinetic energy in the form of bright light. That light is called synchrotron radiation. The energy of the synchrotron radiation lies in the band of a vacuum ultraviolet and high energy X-rays. This vacuum ultraviolet and high energy X-rays are used for characterizing and analyzing the samples in different fields. There are plenty of fields that has been using the synchrotron light. One is biomedical sciences, for the protein crystallography, medical research for cancer radiation therapy, environmental changes like atmospheric research, agriculture for soil studies, mineral exploration for rapid analysis of drill core samples, advanced materials like intelligent polymers, ceramics, light materials, alloys, etc. In engineering, we have imaging of industrial process in real time, and for forensic science to analysis a very extremely small and dilute concentrated samples, right? Due to time, I cannot go through all this thing. We will straightly go through the topic of our interest. So this is one of the real picture of a synchrotron where I worked here for to complete my PhD. This synchrotron facility is at Brazil. It is called a National Laboratory of the Synchrotron Light, and the energy in which the electron was accelerated is around 1.37 giga electron volts. And the synchrotron light we are getting at a wavelength of around 0.6 nanometer, and the critical energy of the radiated photon is around 2.08 keV. So this is a old one, and now Brazil is constructing another one new synchrotron facility that is called Cyrus, the name of the pole star Cyrus, and it is having an energy of around 3 GeV. You can see here what is the size of this machine. So how many people are standing here? It is a so big machine. From this, you can able to get a synchrotron light, and this synchrotron light is used for the characterization of the materials. Right? In India, we are also having the same facility, which is at Indore, Madhya Pradesh, which is called Raja Ramana Center for Advanced Technology. This is shortly known as RRSCAT, in which we are also doing plenty of research using synchrotron techniques. Right? See how a synchrotron light is produced. First thing, we all know that synchrotron is basically a electron particle accelerator. In synchrotron, an electron is fired from the electron gun, and it is accelerated through the linear accelerator, right? And after this linear accelerator, this electron beam is sent into the booster ring. In the booster ring, the speed of the electron is increased, try to achieve the maximum speed of light, right? But now we cannot able to achieve it, but we are trying to achieve it. After gaining the more amount of kinetic energy, it is then fed into the next ring that is called a storage ring. In the storage ring, the electrons keep on rotating, and when it was rotating, it will lose its energy in the form of radiation that is called the synchrotron light. Okay, the first thing here you can able to see it in the Linac accelerator. The electron is fired and it is traveling in the Linac accelerator, and after coming out of the Linac accelerator, the electron bunch will get into the bending magnet. In the bending magnet, the bunch of electrons will get deflected. Due to the deflection, there will be loss in the energy, and this loss in energy will come out as a broad band of synchrotron light. Second thing, if you want a short band of synchrotron light, then the same electron beam has to be passed through the undulator. In undulator, the electrons travel a zigzag path. You can able to see here, the electrons are traveling in a zigzag path. Because of the small turns of the zigzag, a small amount of energy is lost, and we can able to see a small band of short band of synchrotron light. So these are the real pictures of the bending magnet. See how big it is, and these are the real pictures of the undulators. Okay, in undulators we are getting a short band of synchrotron light. In the bending magnet we are getting a broad band of synchrotron light. Okay. And next, coming to this, from synchrotron, you are getting three forms of synchrotron radiation. That is, one is bending magnet radiation, the second one is Visular radiation, and the third one is undulator radiation. So in the bending magnet, the electrons are deflected, so you are getting a broad band of energy, that is h mu, h omega, because their frequency is mentioned in omega because the electrons are rotating in a circular path. So we have to calculate, we have to talk in terms of angular frequency. So we are getting a broad band of energy, and it is having a moderate flux, and it is having a moderate flux. Flux is nothing but the intensity of the radiation. And when the same electron is passing through the Visular, that is having in a zigzag path, then you have a same broad band of energy, that is h omega, and you have a high intensity flux. You can able to see here, the flux was increased when compared to that of bending magnet. But in the case of undulators, you can able to see a very short, narrow band of synchrotron radiation with high flux, with high intensity. So these three types of radiations can be used for our characterizing sample. It all depends upon the nature of the material and depends upon your experimental nature. You can choose this kind of out of these three radiations for characterizing the materials. Okay. Next, what are the puzzles solved so far using this synchrotron radiation? For example, if you take one of the synchrotron technique that is called synchrotron X-ray crystallography. This technique was used to solve the structure of the ribosomes by Dr. Venkatraman, who awarded Nobel Prize in the year 2014 for cracking the structure of the ribosomes. Right. This and second important technique that is one is very interesting is synchrotron radiation X-ray fluorescence. See, this technique was used to analyze the painting of Vincent van Gogh, who is a very famous painter. The painting name was Patch of Grass. On analyzing this painting, there was, to our surprise, there was a portrait of a woman behind this painting. So this conclude that Vincent van Gogh was lived in poverty and he don't have enough money to buy new canvases. So he are using the canvases of a previous painting to paint a new painting. Okay, this kind of historical informations can also be collected by using a synchrotron. When we are analyzing antique samples like this one, right? And the next very important technique of the synchrotron is what we are going to see in the future slides. That is a near-edge X-ray adsorption fine spectroscopy. Shortly, it is known as called NEXUS. In synchrotron, we can couple two techniques and we can get a lot of information. Here, in this experiment, there was NEXUS spectroscopy and scanning transmission X-ray microscopy are the two techniques that was used to analyze a polymer blend. The polymer blend is having two types of polymer. One is saturated and another one is unsaturated. If you closely watch the NEXUS spectra that is given in the red and blue, if you can see the sharp excitation peaks, that is red one, this is due to the unsaturated polymer, and the blue one is due to the saturated polymer. How can we say this? Because in the unsaturated polymer, there will be a double bond. This double bond will undergo pi to pi star excitation, and we can able to monitor this type of excitation at the energy level of less than 285 eV. But if it is in the polymer, if you are using a carbon in the polymer, generally will have a carbon-carbon bond which is having a 285 eV. By using this technique, we can able to tell there are two types of polymer, and one is saturated and another one is unsaturated. This is for the characterization of the sample. In addition to that, when we are using the same sample for the analysis of scanning transmission X-ray microscopy, we can able to see the phase distribution, how the polymers was distributed here in this sample. See, you can able to see this. The white color corresponds to the bright spot corresponds to one type of polymer, and the black spot corresponds to the another type of polymer. When we are changing the contrast of this image, we can get a different image. That is the polymer which is appeared in white, now it appears as black, and the polymer that is appeared in black is now appeared as white. So by changing this, you can able to study the polymer blends, how it was distributed, what is the type of polymer, and the phase distribution of the polymer blends. Okay, so a lot of puzzles can be solved, and it is very interesting thing to use a synchrotron radiation because it is a high energy radiation, and we can crack a lot of problems that are today the world is facing. We can able to do with this synchrotron radiation. What is the difference between ordinary light and a synchrotron light? See, we can do all kind of techniques. Like X-ray diffraction can be using a smaller machine that we are having it handy that we are using in our sample analysis. But what about the synchrotron light? When you use an X-ray of a synchrotron light, what will happen? See, synchrotron lights are very bright. Synchrotron light are 10 million times brighter than the sunlight, and so we can use it for the rapid analysis and the trace element analysis. If your sample is having a very small quantity of elements which are very negligible, cannot be detected by other techniques, you can use synchrotron light because it is very sensitive, very coherent, and high flux, which will it will be able to detect the trace elements in the sample. And the second very important property is the synchrotron light is narrowly focused and does not spread. By using this technique, you can do nano engineering. What do you mean by nano engineering is you can create for example, you can do lithography. What do you mean by lithography is by passing the light, you can create some nano structures on this material where this is used. For example, if you take a semiconductor industry, if you take a chip and you can create a more number of transistors in a small area, then we can increase the speed of our computing. So more number of transistors can be created by using the synchrotron light because it is narrowly focused and does not spread. So like using it like a sizzle to sizzle this sculpture, like we can create a micro and nano structures, right? And the third important property is it includes a broad wavelength range from infrared to hot X-rays. What is the advantage of it? Because of this advantage, we can do chemical state analysis and local structure analysis. What do you mean by that is we can tell the chemical environment of the absorbing atom. In addition to that, we can also tell the spacings of the neighboring atom with respect to the absorbing atom. So we will get a clear picture of about chemical structure, oxidation states, bonding length, bond angle. All this can be obtained by using the synchrotron light, and by based on this data, what you are going to obtain, the techniques are classified. There are plenty of techniques, and we will see one by one. So, these are some of the world famous synchrotron facilities. Not all the countries are operating synchrotron because it is consumes a lot of energy and money. So only a few countries are having a synchrotron facility, and India proud to say that in India is also there is a synchrotron facility. So these are some of the famous synchrotron facility. One is called Petra 2, which is in Germany, having energy of 12 GeV and having the circumference of 2304. This is almost 2 kilometers, right? It was commissioned in 1995, and I don't know what happened. It was decommissioned in 2007. Similarly, there is another synchrotron facility, linear coherent light source, which is in US, which is having an energy of 8 GeV and the circumference around 3 kilometers. Commissioned in 2007, and the very famous one that is called in Japan, that is called SP ring. This is called a synchrotron photon ring 8. The 8 corresponds to the energy of this the electrons is accelerated. Here it is 8 GeV and the circumference around 1436 meters, and it was commissioned in 1997. There is another synchrotron facility which is called Advanced Photon Source in Oregon National Laboratory, US, which is having a 7 GeV, which is having a circumference of around 1104 meters, which was commissioned in 1995. The next synchrotron facility, India is also having a 2 synchrotron facility, that is called Indus 1 and Indus 2, which is at Indore, Madhya Pradesh, at Raja Ramana Center for Advanced Technology. The Indus 1 is having an energy of 0.45 GeV, which has a circumference of around 18 meters. It was commissioned in 1999. The next facility is Indus 2, which is having an energy of 2.5 GeV and having a circumference of around 173 meters, and it is commissioned in 2005. See, in the Indus 2, there are 24 beam lines. That means because of the rotation of the electron, the energy is lost, and this last energy will come out in the form of radiation. So there are 24 experimental hatches. From this, you can have we will have 24 beam lines. These beam lines are unique, and each beam line is used for a separate technique. We can see one by one. The beam line 1, that is called a BL01, the green one, that is called a SAX, which means soft X-ray absorption spectroscopy. This is also called as NEXUS, that what I am going to talk about, near edge X-ray absorption fine spectroscopy, and it is also called as ZANES. ZANES means X-ray. ZANES means X-ray absorption near edge spectroscopy. Why this so many names for the spectroscopy? Because in US generally this SAX is called as NEXUS, that is near edge absorption spectroscopy, and in the European countries it is called as JADES. So all this techniques is using a soft X-ray. The energy of the soft X-ray is around 1000 eV. So what we can do with this 1000 eV soft X-ray? You can able to characterize able to use it for the elements having absorption edge below 1000 eV. So by this you can be able to do this, characterize the elements having below 1000 eV. Then another important technique what we are talking about is extended X-ray absorption fine spectroscopy, that is at the beam line 8. In the beam line 8, what is about it? This is after the absorption edge. If you go further after the absorption edge, then that technique is called extended X-ray absorption technique. That's why it is called extended. After the edge, we are extending, so that's why it is called extended X-ray absorption fine structure. So that technique can be used in beam line 8. Okay. Then another technique, we are going to see only about these 2 techniques, that is called a soft X-ray absorption, that is NEXUS, and another one is called EXUS. I will explain what are the other in a very short time. So this is the beam line 11 is called angle dispersive X-ray diffraction. It is also and we have another option also, energy dispersive X-ray diffraction, that is called in beam line 11. And in the beam line 13, that is called JIX. JIX is called glazing incidence X-ray scattering. That technique can be used in the beam line 13. And the another one is called in beam line 14, you can use a X-ray photoelectron spectroscopy, and beamline 16 we can use a X-ray X-ray fluorescence microprobe. That is we can use the beamline 16 for this, and the very interesting one is beamline 18 because it is called a SWAX. What does it mean is small and wide angle X-ray scattering. This technique is mostly used for analyzing non-crystalline materials, that is biological samples. Right? It will provide information on structure and dynamical process of large molecular assemblies. And the next beamline is beamline 21, which is to study the protein, structure of the protein, that's why protein crystallography. And the last one, which is under construction, I clicked this, make the print shot of this slide on December 3rd, 2018. I don't know whether it is now commissioned or not, but when I was taking the snapshot, it was under a construction phase. So what is mean by ARPS? ARPS is angle resolved photoelectron spectroscopy. This spectroscopy is associated with the energy and momentum of the photoelectron, and we can get information about the band structure. And with this beamline, there is also another microscopic facility that is called a PEM. What does it mean is photoelectron, that means photoelectron emission microscope. Using this, you can able to take images of the Fermi level in the band structure. So these are the facilities that are available in our Indus 2 Synchrotron Center. Next, we are interested in knowing this technique called NEXUS, which is also called a soft X-ray absorption spectroscopy. In NEXUS, we are going to use a soft X-ray that is of energy around 1000 eV or below. Below that, we can use this energy to characterize the elements who is having an absorption edge of below 1000 eV. The soft X-ray, if you look close at the soft X-ray, if you take an atom, for example, at the bottom of this thing, there is a core level. In the core level, there will be core electrons, and there is occupied valence level in which the electrons are occupied, and there is an empty valence cell that are called unoccupied valence cell. When an X-ray of high energy is signed on this atom, what will happen? Two things will happen. One is shown in the red color, and the another one is shown in the blue color arrow mark. In the red color, what is happening? When the X-ray is signed on an atom, the electrons in the core level get excited to the unoccupied valence cell. If it happens, then it is called NEXUS spectroscopy. But in other case, if it is not happening, and instead of getting electron from core electron to the unvalence cell, if the electrons get ionized, if photoelectrons are released, then it is ionizing excitation. In the ionizing excitation, if the electrons that is emitted from the valence cell, then it is called ultraviolet photoelectron spectroscopy. In short, it is called as UPS. If the same electron is coming out from the core valence cell, that is in the blue color, then it is called XPS. We are not interested going to learn about this ionization excitation. We are interested only in the NEXUS, which is for a few minutes after the fall of few seconds after the fall of X-rays, it is in the neutral excitation. But even after neutral excitation, there will be two types of autoionization will take place. One type is called participator decay, and another one is called spectator decay. In the participator decay, what will happen is the excited core electron, right, which occupies the unoccupied valence cell, will return to the core level. While it was returning, it will release an energy. That energy will kick an electron from the occupied valence levels. Occupied valence level. If it has happened, then it is called participator decay. In other case, if this core electron that is excited from the core level to the unoccupied valence level, it will remain there. By taking this energy, one electron in the occupied valence level will be emitted and release the energy. By taking this energy, the electron neighbor to this valence electron in the occupied valence cell will return to the core level. If it has happened, then it is called. Then if it has happened, then it is called spectator decay. There are two types of decay that will happen in the NEXUS spectroscopy. Okay, so we are much interested in NEXUS spectroscopy. What is the thing you have to keep in mind? There is a neutral excitation, right? After that will go for two types of autoionization. One is called a participator decay, and the next one is called the spectator decay. So this is a typical NEXUS spectra, right? That was taken for carbon monoxide. We all know that carbon, which having electronic configuration 1s2, 2s2, 2p2, and oxygen will have 1s2, 2s2, 2p4. When it is undergo bonding in carbon monoxide, there will be formation of 2 pi bonds and 1 sigma bond. So the 1s and 2s electrons are buried deep into the core cell. So there will be depends upon the energy of the supplying incident X-ray. It depends. It will be excited. For example, if you supply energy equally in the valence level. In the valence level, the electrons will undergo pi to pi star excitation, and you can able to see a sharp peak here. That is due to pi to pi star excitation. That is by it is having a 2 pi bonds in the carbonyl molecule. Then after the pi to pi star excitation, then there will be sigma to sigma star excitation. You can able to see some kind of small peaks that are due to the Redenberg states. These states are very difficult to monitor in the real time exospectra because these energy levels are very close to each other, and we cannot be able to distinguish it. Okay, sometimes so we cannot able to monitor this kind of excitations. So two kind of things excitations can be clearly monitored. One is pi to pi star, which is having a sharp peak, and it will always first appears first in the nexus spectra, followed by sigma to sigma star, which is a very broad spectra. Similarly, it is a very strong. Sir, can you please mute the mic, please? Please. Okay. When we are doing. Okay. So next we will have a excitation called sigma to sigma star, which is a very broad excitation. Okay, these are the this is an ideal spectra of a carbon carbon monoxide. Okay, so two types of this X-rays can be monitored in two ways. One is called transmission mode, and another one is called electron yield mode. When you are doing a transmission mode, the sample what we are using has to be very thin. Okay, so that the X-rays can pass into the sample, and we will get more information regarding the bulk of the sample. That is what is inside this sample. That is called bulk of the sample. But when we are using this electron yield kind of method, you can get informations on the surface of the material. You can mainly interest in the surface. Transmission mode is for to study the bulk of the material, and the electron yield mode is for studying the surface of the material. What will happen in the surface heat of material is, if the sample is considerably thick, that is shown in the blue color, which is mounted to a metal conducting material, and this metal is grounded through a picometer, right? Because why do you have to picometer? Very few amount of current will flow, so that's why we are using picometer to detect that current. Okay, what will happen here is, when we are passing a X-ray, that is the blue one on the sample, the X-rays penetrates deep into the sample and ionize the atom and create photoelectrons. These photoelectrons cannot escape, so it will create it bombard with the next atoms, and it will produce large number of secondary electrons. So the secondary electron that is on the surface will flow through this ammeter to the ground. By monitoring the current in the ammeter, we can able to tell what type of chemical morphology, what type of chemical morphology, what we can able to study the surface properties of the material. Okay, by monitoring the current in the picometer, we can tell the surface properties of the material. So there are two modes. One is transmission, and the second one is electron yield mode. Transmission is to study about the bulk property, and the electron mode is to study about the surface properties of the material. Next, what is the difference between the XPS spectra and nexus spectra? We are all familiar with the XPS because we are studying in our undergraduation and post-graduation regarding X-ray photoelectron spectroscopy. We are much familiar about it. And what is the main difference? Because both are using X-rays, and both are X-ray techniques. And what makes the differences here is, but it is an emission technique, but here in nexus the atom is not emitted. Atom remains in the neutral state. Okay, but we can get very clear information in the nexus. For example, if you take a polyimide polymer that is shown in this white color here in the insert image of the nexus spectra, in this polymer there are four different atoms. One is nitrogen, second one is oxygen, third one is carbon, and fourth one is fluorine. In the exospectra and nexospectra, you are getting elemental peaks for all these four elements, and you can able to see it. So four peaks has been there, one for fluorine, oxygen, nitrogen, carbon. Similarly, in the nexospectra, you can able to see carbon, nitrogen, oxygen, and fluorine. But if you watch the peaks very carefully, what is there in XPS spectra, all the peaks are single peaks. But in the case of a nexus spectra, there are multiple peaks. So what information this nexus spectra is giving? That means, for example, if you take a carbon, there are 3 or 4 peaks in that. Means that the carbon is attached to 4 different types of atoms. That is, 4 different types of bond are formed because of the attachment with the different atoms. But if this kind of information cannot be obtained in the XPS spectra, but you can obtain. When you can obtain is by deconvolution of the nexus XPS spectra, you can get some information. So it is a time-consuming process. You have to deconvolute. You have to go for curve fitting method, and you can able to see what is inside the XPS spectra. But in the nexus, you will get a clear thing, because if, for example, if you take nitrogen here, 3 types of bonds here. So this nitrogen is attached to one benzene ring. This nitrogen is attached to the same benzene ring and with a different and non-aromatic ring, and this nitrogen is attached to close to 2 carbon. So there are 3 different nitrogen atom, 3 different bondings with respect to nitrogen, and you can able to get it 3 different. Similarly, for oxygen, you can get it here, and you can see only one single peak in respect to fluorine, because all the fluorine atoms are connected to the carbon atom. So from this, this is one of the main advantage of nexus spectra over XPS. Okay. And the next one is, the nexus spectra can also use to analyze the building block of the polymers. For example, if you take 2 polymers, that is polyethylene and polyethylene oxide, the first figure, this central carbon is attached to 2 carbons and with 2 hydrogen. But in the case of polyethylene oxide, the central carbon is attached to 1 carbon and another one is attached to oxygen. You can see the difference in the spectra. We all know that oxygen is having a high electronegativity than carbon atom. So the nexus spectra is shows a little bit of there is a deflection from in towards the higher energy, right? Then there is a very big difference in the splitting, right? The small shift towards the higher energy, and because of the shift is because of the higher electronegativity of the oxygen atom, right? When coming to the next spectra, which is having a nylon and a polymethyl methacrylate, nylon is having is bonded to nitrogen atom. In polymethyl methacrylate, the carbon is attached to the oxygen atom. We all know that oxygen is more electronegative to nitrogen, and the difference between the electronegativity is very small. So the shift is very small here. See, you can see here at the center there is a very small shift, but that is for a higher electronegativity atom, the spectrum is shifted to higher energy. Okay, so we can able to characterize very small changes in the chain of the polymer can be easily recorded by using this technique. And the next one is one very interesting is polystyrene and polyimide. In the polystyrene, the carbon is bonded to the hydrogen. In the case of polyimide, the carbon is bonded to the nitrogen. This will give a very characteristic peak at 286. That is corresponds to the excitation of the carbon-nitrogen bond electrons. So you will have a new peak at around 286 eV. So by this way, the building blocks of the polymers can be clearly understood. In addition to that, when we do a deconvolution, this is I told you this is a very difficult process, because the spectrum after the edge, the background correction is very difficult. You have to apply some mathematical function to solve this. So when you do a deconvolution, you will get plenty of information regarding the bond excitation, pi to pi star, and what type of bond is there. All these thing information can be obtained in the using this nexus spectroscopy. In addition to that, if you look for self-assembled layers, for example, some molecules are get absorbed on the metal surface, and we can able to tell what are the how the molecules are oriented in the on the metal surface. That means that what is the angle of tilt. It is the see here the angle of tilt is 57 degree with respect to this molecule OPA, and that is when it is 26 degree with respect to another molecule. Like that, we can able to tell the self-assembled monolayer how it is oriented and what is this how it is positioned on the surface of the material. Okay, all these informations we can get through this nexus spectroscopy. This is one of our nexus spectra that what we have taken for the polypropylene. And when we deconvoluted this polypropylene spectra, we have get 6 types of excitation. That is, one is corresponds to sigma star carbon hydrogen bond, which is the position at 287.3, and we get sigma star, another sigma star CH bond, that is for Redinberg state also. We cannot able to distinguish which is sigma star CH or Redinberg state, because I already told you they are very close, and it is around 287.8 eV, and we are having an excitation unable to detect, that is at 288.1 eV, and we have pi star carbonyl excitation at 288.6, and we have sigma star carbon carbon excitation 292.5, and another sigma star carbon carbon excitation at 298.6. See, what we have done is we have chosen this energy, excitation energy of around 288.7, and we irradiated the polymers with this energy for different time intervals. This is for 1 minute, and this is for 5 minutes, and this is for 15 minutes, and this one is for 35 minutes. When during this irradiation time, we can able to see this yellow peak that is corresponds to carbon monoxide, because we are irradiating the polymer in the presence of oxygen. When we are doing this irradiation, this oxygen is the bonds in the polymer is broken, and the carbonyl bond is forming on the surface of the polypropylene. This is very clearly reflected here. For a 35 minutes irradiation, there is a peak, very, very strong peak, which is corresponds to 288.6, corresponds to the 5-star excitation of carbonyl bond. Is clearly understood that when we are irradiating this technique, see, when we are irradiating with a soft X-rays, some bond breaking will have also takes place, and we can use this concept for surface functionalization. Okay, so using NextSurf, we can do surface functionalization as well as we can do characterization by using this X-rays, and we can monitor that surface character functionalization by using NextSurf spectroscopy. And another one is we have also used NextSurf for characterization of inorganic materials. What we have done here is we have created a super hydrophobic surface using titanium dioxide nanoparticles and a saline solution. We used two types of saline solution here. One is saline solution in water, and one is saline solution in xylene. When we are treating the saline solution with titanium dioxide, the silanes get absorbed on the surface of the titanium dioxide, and a super hydrophobic surface is created. But to understand what is happening on the surface, we go for NextSurf spectra. This is shown in the figure 5, which is a NextSurf spectra of oxygen oneness curve, which is curve fitted. Okay, we curve fitted for the 3 spectra. One is for untreated titanium dioxide, which is at the top, and the middle one is a treated titanium dioxide with the silane in water, and the third one is treated titanium dioxide with silane in xylene. If you closely watch the NextSurf spectra, you can able to see the T2G EG spectra of untreated titanium dioxide having some intensity. When the titanium dioxide is treated with silane in water, you can able to see a very strong peak of sigma star OSI bond, okay, which is greater than the titanium dioxide. This shows that what is happening in silane in water is the silane is undergoing polymerization, and this polymers will deposited on the surface of the titanium dioxide and not uniformly distributed. It is in the form of patches, and you can get a very strong peak of sigma star OSI. Similarly, when you are coming for the third spectrum, that is a titanium dioxide treated with silane in xylene, we know that in xylene there is no formation of oligomers. That is, silane cannot able to undergo polymerization and form oligomers. So silane remains as a molecule, and it is uniformly distributed all over the titanium dioxide. So you can able to see here the peaks of T2G EG of titanium dioxide and the sigma star OSI bond. Okay, they are of equal intensity. This shows that in titanium dioxide treated with silane in xylene, there is a uniform absorption and there is no polymerization. But in the case of titanium dioxide treated with silane in water, there is a polymerization is taking place. So this kind of very clear-cut information can also be obtained by using a NextSurf spectroscopy. And the third one is polarization dependent NextSurf spectroscopy. What does it mean, polarization? We all know about polarized plain polarized light, in which the electric field vector is always in one direction. So when we are using a plain polarized light, X-ray light, and when we are inciding on a material, right, we can able to study the materials that are get absorbed on the surface. For example, if you take here, benzene was get absorbed on the silver 110 plane. Okay, so when it is absorbed on the lying flat on the surface of the silver, in benzene there are two types of bond. One is sigma bond and another one is pi bond. The sigma bond is in plane with the benzene, and the pi bond is out of plane with the benzene. When you are passing a plane polarized X-ray, you can have this, the electric field vector of that is shown here, the first picture. The electric field vector of the X-ray will interact with the pi bond of this benzene, and it will use only the spectrum related to pi bond. and there is no interaction of this electric field vector with the sigma bonding. So you don't get any sharp peaks related to sigma bonding. But when the same electric field vector lies parallel to the sigma bonding, then you can get only the information relating to the sigma bonds, and this technique can be used to find out whether there is a how the absorbed molecules are get absorbed on the surface of the material, right? And the next one is called angular dependence X-ray nexus spectroscopy. What does it mean? We know that due to the plane polarization, the X-rays is having a electric field vector. So, for example, if you take a carbon monoxide molecule that is get absorbed on a surface, there are two kind of orientation. One is it can able to lie parallel flat to the surface, that is lie parallel to the surface, and another one is it can lie able to perpendicular to the surface. If it is like parallel, for example, and you are passing an X-ray having a electric field vector parallel to the magnetic dipole moment, that is called denoted by the symbol M. If it is parallel, the electric field vector of the X-ray and the magnetic dipole moment align parallel to each other, then you can able to say there is a strong signal, intensity signal, nexus spectral signal will be obtained. So by this way, you can able to tell that the material by grazing on the surface, you can tell that the material is carbon monoxide is get absorbed parallel on the surface. If the carbon monoxide is absorbed differently, for example, maybe a perpendicular or some tilted angle. In this case, the electric field vector of the incident X-ray is does not lie parallel to the magnetic dipole moment. On solving this, the resultant vector will be very a different one and will have a less intensity. So you are having a small red spectrum here, and this tells that the molecule is not aligned, is not parallel to the surface, and it is aligned perpendicular to the surface of the material. So you can get this kind of informations by using this nexus spectroscopy. So coming to this, now we are going to compare near edge X-ray absorption spectroscopy with the extended X-ray absorption spectroscopy. In near edge absorption spectroscopy, we can able to get information regarding to the absorption edge. So this will give information like chemical environment of the absorbing atom, that is the region denoted here. So this is associated only with the close to the edge. That's why the spectroscopy is also called as near edge. What is happening near the edge, that is monitored by using this Zeiss spectroscopy, and you can able to see a clear spectra because here the electrons are not ionized, no photoelectrons are created, so the molecule remains neutral and you can get a clear spectra. But when you are observing after the edge, that is called extended X-ray absorption fine structure, because here photoelectrons is created and this photoelectron will get collided with the neighboring atom, and so there will be a lot of noise signals will be created. So interpreting the XF spectra is a little bit difficult because you have to filter the noise by using the filters and you have to apply this technique. So when you compare to Zeiss will use the information regarding the chemical information of the absorbing atom, and in the XF you can get the information regarding the spacing of the neighboring atom. You'll get the spacing of the neighboring atom. But XF is very difficult to interpret. But in the case of Zeiss, it is very easy to interpret because there is no photoelectrons are emitted because the atoms remains as a neutral. Okay, so we are using a transmission technique here for determining this two Zeiss and the XF spectrum. See, and comparing the Zeiss and the XF spectra, what information you can get, right? Both are synchrotron techniques. Both are using X-rays, and Zeiss, which is comes under which is we can use it in situ, right? I told you one example of the surface functionalization of polymers using oxygen, right? Using irradiating with high energy X-rays. One such we can do suitable under reaction conditions. We can do in situ experiments, and this for characterizing the samples, we does not require long range order, and both are element specific, right? Well, the main advantage of the Zeiss spectroscopy is we can get the information regarding symmetry information of the absorbing atom